Good morning, everyone. We hope you all are excited for the day 2 of conference. Nice energy, thank you. So our first speaker, as you could see here, is Ivan Blinkov, who is a technical leader with over a decade of experience in data storage. Has been instrumental in the database systems such as ClickHouse and now YDB. As the VP of Product and Open Source at YDB, he's driving innovation with this versatile distributed SQL database. You could see that here. This is going to be perfect for mission-critical workloads. Today, Ivan will walk us through YBD's game-changing features, from handling complex data-driven applications to its seamless deployment options. So please join me in welcoming Ivan.
Thank you. Hi, everyone. Yes, my name is Ivan Blinkov, and I was introduced already. So let's jump into it. Today's talk will consist of 3 main parts. First, we'll explore what's YDB and what it can do in main use cases. Then we'll see high-level architecture around how it works and what to expect from it. Then we'll take a closer look at a couple of interesting technical details. And finally, we'll see how YDB fits into broader overall open source ecosystem. So as the talk title says, YDB is an open source distributed SQL database. It's designed for business critical applications that have really strict requirements on both data consistency and availability. To accommodate this, YDB provides distributed transactions that provide serializable isolation level by default, which is stricter than most other DBMS do. And also it automatically survives hardware issues, even major ones like the whole data center is going down, while maybe you have maintenance in some other one, or also one rack, another data center is also unavailable. Initially, YDB started as transactional database, but over the years, it grew to be more like data platform with a bunch of extra features like column-related tables for analytics, topics similar to Apache Kafka topics, federated queries, and so on. On the slide, you can see typical industries that use YDB, and also a bunch of user logos that you likely won't recognize because they're from different parts of the world. But the point here is that these kind of requirements usually come from 2 things. It's either directly managing business data, so like financial transactions, orders in e-commerce, taxi rights, clicks on advertisements, and so on. So when you have direct impact of your data unavailability or outages to your business and your revenues. Or by second option is if you provide low-level infrastructure for other businesses to rely on with similar consequences. On the slide, you can see key milestones in YDB's history. But the key takeaway here is that YDB is a pretty mature technology with well over a decade of development invested into it. But it's only 2 years in open source under Apache 2.0 license, which is one of the most permissive open source licenses, allowing even commercial use for free. And we'll briefly touch other topics later in the talk. So how YDB works? First of all, to accommodate these kind of requirements, it normally is running on a cluster. And in most cases, these clusters span multiple data centers to accommodate these kind of outages. YDB clusters consist of 2 main nodes, compute nodes highlighted in blue, and storage nodes in purple. Let's quickly walk how a typical SQL query path works. This cluster provides for outside world a few like common APIs. So on the slide you can see the YDB native one. It is based on gRPC, which is a common cross-service communication library that provides code generation for both clients and servers. And for clients, we also provide SDKs that basically wrap these generated clients to add some features that are useful for applications talking to databases like proper read-writes of transactions, load balancing, and so on. So once the request comes to the cluster, to the proxy component, it gets passed to the query processor, which is the kind of orchestrator of the whole query execution. So it, in a distributed fashion, it understands which other components need to be involved to produce the request result. often it needs to execute a distributed transaction with a separate mechanism we will quickly return to later. And most of YDB features are implemented in a framework we built that we call tablets. So a tablet is a lightweight user space process so you can have much more tablets in a system that you could have operating system threads. And these tablets talk to each other only via message passing. This is similar to actors you can find in Erlang, Akka, and similar technologies. And each tablet has its own private state that it stores on reliable distributed storage. So also with all this redundancy. And basically distributed storage is specialized, so it's not some external third-party thing. It's a specialized system that's designed specifically to store tablet states. And also fun fact, it stores data not on file system of sorts, but it directly works with disk drives via block devices and tries to leverage their physical properties to do it efficiently. So that's the second part. We'll take a closer look later. So, and this design allows these tablets to easily move between nodes because you can kind of always restore its state from remote storage. And this allows for two main things. First, it allows you to restart this failed process on another node in case of any failure. So if some issue with the node, you can easily continue processing what you are doing somewhere else. And also for load balancing, because if some node is overloaded, again, you can free it up by moving some tablets from it. So all YDB features are, not all, but most YDB features are implemented as tablets. For example, there are tablets responsible for subsets of rows of row-oriented tables. There are tablets that are implementing partitioning of topics. They're similar to Apache Kafka topics. But each instance of tablet is managing only a small subset of data. So this kind of logical entity of a table or a topic is what people are working with, but they don't see these implementation details. And that's what allows them to kind of easily work with large amounts of data that automatically adjusts to whatever environment is currently happening in the cluster. So let's take a closer look at the distributed storage layer. So it provides two main operating modes. I was mostly talking before about the left one, Mirror 3DC. So it's a cross-cluster mode that provides the most resilience in terms of fault tolerance. But because it's basically copies of data, so replicas, it provides 3 times space amplification. So you need 3 times more disk storage, disk capacity to store each logical piece of data. And also YDB has alternative kind of compromise mode called Block 4.2. It's designed for a single data center operation, but with still reasonable level of fault tolerance, so you can survive 2 server racks going down and still continue operating, accessing your data as if nothing happened. And there are a couple more reasons you might choose this right one. So first, it's less space amplification, so it needs only 50% more disk capacity compared to the logical data. And second is this distributed transaction. They require multiple network hops to execute, and inside single data center, it leads to lower latencies of transactions than comparing to going between data center for each transaction. Let's see how Mirror 3DC works, the first topology. So you can see we have 3 data centers and 3 nodes in each data center, ideally in separate server racks. So this kind of minimal setup that makes sense, and we'll see why in the next slide. And to explore how this works, we'll use write operations as an example. So in normal case, when everything is working fine, it's simple. You choose 1 node in each data center and write a copy of data to it. You've got 3 copies. You can survive these requirements of going, these requirements of availability. So, but the interesting thing starts to happen when failures start happening. So if you have large enough cluster, you might have disk failures and node failures happening daily, and full data center outages are also not something unheard of. So in this case, let's imagine we have a fire in data center 2. It's hard to see now, but and maybe you have maintenance going on node 7. So in this case, we need to write 4 copies of data to continue maintaining these guarantees of surviving these kind of outages. Anyone has idea why? 4? No? So it's to continue accommodating multiple failures like this going one after another. So let's imagine this previous failure was resolved somehow, and immediately or shortly after it, another similar one happens in different data center and different another node. So if you wrote on the previous slide only to 3 copies, you might get unlucky, and the third copy would end up on node 4, and you will lose read access to your data. But in this example, node 1 is the kind of surviving one from the previous write that will still allow you to read back whatever you originally wrote. And then similarly, after this new failure happened, or new write operations will still be able to find 4 more nodes to continue doing the same thing over and over, and thus always providing you access to your data no matter what. Like as long as you stay in this inside this failure model. So a single data center block 4.2 works similarly, but it uses a different approach. So instead of copies, copies of data, it uses an approach called erasure coding. So basically, it's an approach when you split, kind of create 6 parts out of your original piece of data. It's 4 data parts and 2 parity parts. And there is a bunch of math that's based on Gola fields, if anyone into it, that allows you to restore the original piece of data from any 4 parts out of 6. Basically, this allows you to lose any 2 server racks and still get access to your originally written data. And if you were wondering why 8 nodes and not 6, it's because you still want to continue having 6 separate server racks to write new 6 parts, even if the outage is happening right now. The second technical highlight I want to give is transactions. So distributed storage we just explored is providing reliable storage of state of each tablet. And from the user perspective, you'd want to have transactions not inside one single row, but between rows of single tables and between different tables, between topics and tables, and so on. So you need transactions that are kind of global, involving multiple tablets at the same time. So that's why we have separate mechanism for doing this. And also, yeah, YDB provides more strict guarantees than many other databases for this, called serializable isolation. So the initial implementation of these transactions were based on this research paper that's cited in the bottom. The paper is called Kelvin. It's from Yale University. And it introduced an algorithm that's called deterministic transactions. It's in nature similar to Raft and Paxos that are more widely known. But in general, it fitted better the requirements of YDB had at the time. But there's one big downside, that it limits what kind of transactions can be executed using this approach. So for instance, it requires you to know in advance which subsets of keys or table rows will be part of transactions before you start executing it. And in real world scenarios, that not always viable to know this in advance. For example, you might have secondary index that you use to resolve which keys you need to read from the main table, and thus you figure out the keys along the way. So initially, we had this requirement exposed to end users, but over time, we built these 2 extra mechanisms, optimistic locking and VCC, to allow a wider range of user-level transactions that basically use deterministic transactions as a building block to execute multiple of them and still check that everything is correct as user requested. So check the paper if you're interested. And the last part is about YDB in open source. So when the project was originally open sourced, it already had its own ecosystem, which also was open sourced SDKs and integrations and so on. But one of the first things users requested was integrations with other ecosystems. That's why we invested into PostgreSQL compatibility mode and Apache Kafka compatibility mode. And similarly, historically, it was mostly deployed using proprietary deployment tools, but now we're working actively on basically we have Kubernetes separator and Ansible playbooks to deploy with more widely used approaches globally. Same goes for integrations with observability and data management. So these are just examples of technologies we integrate with. I have only a minute to cover this how Postgres compatibility mode works. So basically, we take clients from PostgreSQL ecosystem because we want to be compatible with them. We had to re-implement PostgreSQL wire protocol because the original implementation is kind of weird because it forks operating system process for each client connection, which is resource intensive and doesn't scale. We took the components that implement most of semantics of how SQL queries are executed from Postgres, but reused all our infrastructure with tablets and storage and transactions to provide all these properties people care about when they choose YDB. To wrap things up, we are looking for contributors. So the core platform is built from scratch in C++. We have Kubernetes separator, Ansible playbooks, SDKs in all major programming languages, documentation Markdown. If you're into stuff like this, please go check it out on GitHub with QR code. Or you can find us as YDB platform. That's it. If you have any questions, you can find me upstairs. We have a booth there. Or you can connect with me on LinkedIn. My name is Blinkov. Thank you.
Any questions?
Yeah, that was a nice talk. I wanted to ask you more about the Apache Kafka compatibility that YDB has. What does that mean?
Yeah, basically YDB has its own API that's kind of similar to what Apache Kafka has. It's also based on gRPC, and it was designed to make it easier to provide exactly one guarantees, which is kind of important in this space. So you don't have duplicates or lost messages. So yeah, but again, like one of the first things in open source that people request were kind of compatibility with client libraries that they are used to. So basically, we have another API that takes a wire protocol that Kafka's client libraries expect and implement the same server side for it, and then translate roughly to the same execution path the YDB topics infrastructure expect, and it looks closely similar. Yeah, that's kind of what it is. It's CP. The question is what part of CAP theorem is it reliant on, and basically it's gets the closest to CP part of it. Yes. So we use optimistic locking and multi-version concurrency control, so it looks similar to what you would expect from other databases like Postgres and others.
Hello. 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 Am I audible? Yeah. So you mentioned that that you need to write to at least 4, where the other node is in a different data center, right? In your 3 data center architecture. So when the 2 nodes that were down before come back up, you're going to replicate to those 2 again when it's up?
Because you have time to do that, and failures might happen frequently enough, so kind of you're unlucky.
So in case if your reads come in before the replication happens, how do you decide which node to send the reads to?
If all reads, well, actually it's a little bit more complicated because there are multiple modes of reads, and these tablets can decide what read mode to use. And actually, for example, they might read all copies just to take the minimal viable amount to produce faster, to get the fastest responses, and also they can go slower if they care about overall throughput rather than latency of each particular read. So it's kind of depends on business logic. On top of it, like on higher levels, on how to handle this.
Thank you.
Hi, I had a small doubt about the database thing. So do we have to have a separate special configuration to set this distribution up, or does it happen natively? And also, when you do a write operation, let's say some kind of a locking write, so I'll just repeat my question. So to configure this, do you have to specially configure anything on each node level? And let's say you have a write, like a locking write. So how will it handle across each and every worker? So will it be locking all the workers at the same time, or how does it work?
This locking, it works not on workers. It basically checks correctness of the overall transaction. So it works not on workers. It works on ranges of table keys, like because they're all kind of ordered by primary key. Yeah, and that's for configuring each node. So obviously there might be some operating system configurations you might want to make just to make performance better. But in general, the trickiest part here is that nuance I mentioned about working with raw devices. For example, I had another talk a few weeks ago in Hong Kong about how to pass block devices from your host machines to Kubernetes. They have like 5 ways to do it with different trade-offs. Yeah, so obviously there are some nuances around it, but in general, all this sharding and something basically boils down to choosing which of these topologies you actually care about. So they're kind of the main one we recommend. And it's cluster like administrator, DevOps, whatever you call him, needs to choose like which kind of way you want to go depending on how much hardware you have, how much space and latency requirements you have. So that's kind of the main thing. And after this, it's like nothing way too special. So basically all sharding is happening automatically. So from application standpoint, you're just working with a petabyte size table, and it somehow load balances, self-heals if something happens. So it's not application developers' problem to how all this happens.
And as you just mentioned, your isolation level is by default serializable, right?
Yes.
So it will be, yeah, that's where you said optimistic locking. So it's going to lock before it does any kind of conflicting write, right?
No, actually optimistic means the latter. So basically checks on commit that everything is still okay. And there are trade-offs around this. So you might like hope that it happens, but so it's like with pessimistic, optimistic, like in normal life. You might hope that it will happen, but you'll be not so good surprise in the end. Or you might be pessimistic in the beginning and not even try. So depending on the workload, it has some performance properties, and you might need to retry if you ended up. So there's specific error code that says, hey, you need to retry this. And you might see it in this approach, but it happens like on commit and not on first of operation. So it's different from some other DBMS that do pessimistic locking.
Thanks for resolving the query. Thank you.
Thank you.